Wow. Laplace transforms, chapter 8. So this is the last big topic in our course, and it uses some very beautiful integration, mathematical analysis. And we have to understand from Calc 1 and 2 a little bit about improper integrals over an infinite interval. But the Laplace transform of a function f, which is a function of t defined for t greater than or equal to 0. We don't see the values of the function f for negative t. So f is a function defined for t equal to greater than 0. Let s be a real number. And then the Laplace transform of f is the function capital F of s, which is defined to be the integral from 0 to infinity, e to the minus ft, f of t dt. So you're integrating with respect to t, and the integrand involves this number s, so you get some, so this integral is a function of s. So capital F of s is this function of s. And again, just to remind you about what an improper integral over an infinite interval means, this is the limit as capital T goes to infinity of the integral over the finite interval from 0 to t, e to the minus st, f of t dt. So we have two problems. One, given a function f of t, compute the Laplace transform f of s, which I'll sometimes write as script L of f. That means capital F is the Laplace transform of the function little f. And the second problem, you might call this the inverse problem. Given a Laplace transform f of s, find the function little f of t such that f of s is the Laplace transform of little f. So for example, suppose we take the function f of t just equal to 1. What is the Laplace transform? Capital F of s is the integral from 0 to infinity, e to the minus st, 1 dt. That's the limit as t goes to infinity, the integral from 0 to t, e to the minus st dt. But we know what this integral is. We're just integrating an exponential. This is the limit as t goes to infinity, the integral of e to the minus st, if s is different from 0, if s equals 0, this is just an improper integral. It's infinity. It doesn't exist. But this is minus 1 over s, e to the minus st from 0 to t. Let me just continue over here. So this is the limit as t goes to infinity of what? When you evaluate this at capital T, you get minus 1 over s, e to the minus s capital T, minus, and when you evaluate this at 0, you get minus 1. So minus minus 1. So this is minus minus 1 is plus 1. This is the limit as t goes to infinity of 1 minus 1 over s e to the minus st. So let me write that down again on clearly. So if you have f of t equal to 1, the Laplace transform of f is the function f of capital F of s, defined to be the integral from 0 to infinity e to the minus st dt. That's the limit as t goes to infinity of 1 minus, what did we have? 1 over s e to the minus st. What is this limit? Well, it depends on s. It depends on s. If s is 0, this doesn't exist. If s is negative, minus s is positive, this goes to infinity. So the only time you get a finite value for this is when s is positive, and then, oops, did I make a mistake? I'm sorry. Yeah, here, when t is equal to 0, I get minus 1 over s. So this is minus minus 1 over s. So this is 1 over s minus 1 over s e to the minus st. And this equals what? This equals 1 over s if s is positive. So the Laplace transform of the constant function 1 is 1 over s for s positive. And the function is not defined for s negative or 0. And what about the inverse problem? Suppose if the Laplace transform of L of f is equal to 1 over s for s greater than 0, then f is equal to the constant function 1. So if you're given the constant function 1, the Laplace transform is defined for s positive and it's equal to 1 over s. If you're told that 1 over s is the Laplace transform of some function, then the function is 1. Okay. So, and let me just emphasize one thing, that is, in calculating Laplace transforms and inverse Laplace transforms, it's useful to have a table of these things. And there is a table in your book. So let me just show it to you if you haven't looked at it yet. Share screen. Here we are. So you should see page 461 of your textbook. Oops, sorry, that is page 461. But that's not the page that I want. What I want is the end of chapter 7. Where is that? Sorry, the end of chapter 8 on Laplace transforms. There it is. So on page 463 of the text, there is a brief table of Laplace transforms. So here's the one we just calculated. If little f of t is the constant function 1, the Laplace transform is 1 over s. And for other functions, here's the Laplace transform. If you take the cosine of omega t for any number omega, the Laplace transform is s over s squared plus omega squared. Or the function e to the lambda t sine omega t, this is the Laplace transform. And there are 2 pages of Laplace transforms. And you should be looking at this constantly, especially when dealing with inverse, whether direct or inverse problems. Given a function, to find the Laplace transform, You can look it up. Given a Laplace transform to solve the inverse problem, you also use the table. And I'm going to spend today working out examples of all this. Okay. Any questions before we continue? Now, for very elementary functions, it's expected that you can compute the Laplace transforms yourself without even looking at the table. So if you see an exam problem to find the Laplace transform of a function to calculate it and show your work, then you really have to calculate it and show your work. So let me do another problem. Suppose we have f of t equal to t. Then the Laplace transform of f of s is the integral from 0 to infinity e to the minus st t dt. So to calculate this, we need to find the indefinite integral of e to the minus st t dt. And we can do this by integration by parts. What are parts? Well, I can have t e to the minus st. The derivative of t is 1. The integral of e to the minus st is minus 1 over s e to the minus st. So the first thing we remark is we only can do this for s different from 0. So then this integral, the indefinite integral, is this times this minus t over s e to the minus st minus the integral of this times this, which is minus 1 over s e to the minus st dt. So this is minus t over s e to the minus st. Minus times minus is plus. I can take the 1 over s outside. Integral e to the minus st dt. Which is minus t over s e to the minus st plus 1 over s. And what's the antiderivative of e to the minus st? Again, it is minus 1 over s e to the minus st. So what I get is minus t over s, and here I have minus 1 over s squared. And if I factor out e to the minus st, this is what I get. So this is first year calculus. This is the indefinite integral. So if I want to take the integral from 0 to capital T of e to the minus st dt, that's equal to this. Evaluated from 0 to capital T. When s is equal to capital T, I get minus t over s plus 1 over s squared e to the minus st. And when t is 0, I get minus times minus is plus. I get plus 1 over s squared. And then I want to take the limit as t goes to infinity. Because my Laplace transform, this is the limit as capital T goes to infinity, integral from 0 to t, e to the minus st dt. As capital T goes to infinity, if s is positive, this goes to 0. If s is negative, this goes to infinity. So this integral converges only for s positive, and this is equal to 1 over s squared for s greater than 0. So this is a proof that the Laplace transform of t is equal to 1 over s squared. Okay. Again, I did this example last week, and I'm doing it again because this kind of mathematical technique is very important for you to master. Let's do one more example. Let's take a trig function. Actually, let's do two more examples. One would be easier than another. Suppose I take an exponential function, e to the at. Then the Laplace transform is the integral from 0 to infinity, e to the minus st, e to the at dt. But this is just an exponential. This is the integral from 0 to infinity, e to the minus s minus at dt. What is the integral of e to the s minus at dt? It's minus 1 over s minus a, e to the minus s minus at. And I want to evaluate that from 0 to infinity. Now, if s is equal to a, this is not defined. So s can't be equal to a. If s is less than a, s minus a is negative, minus that is positive, this goes to infinity. So this integral only converges for s greater than a. And if s is greater than a, as t goes to infinity, this goes to 0. And when t equals 0, it's plus 1 over s minus a. So the Laplace transform of e to the at is 1 over s minus a for s greater than a. Any questions about this? Okay. Well, here's another example. And in this case, I could do it by hand, but I'm going to use the table instead. Suppose I want to find the Laplace transform of t cubed e to the 4t. So let me look at my table. Here it is. I have the function t cubed e to the 4t. Aha. I have t to the n e to the at is n factorial I have this from the table. Let me just write it down. Let me stop the share. So from the table, it says t to the n e to the at, and its Laplace transform is n factorial over s minus a to the n plus 1. Now, in this case, I have t cubed e to the 4t. So this is n equal to 3, a equal to 4. So the Laplace transform immediately from the table is n factorial over s minus 4 to the 3 plus 1 to the 4th power, or 6 over s minus 4 to the 4th. Any questions about this? Now, we have the Laplace transform of a function little f is the integral from 0 to infinity e to the minus st f of t. And if we had another function, little g of t, the Laplace transform would be this. And if both of these exist, then you would say that the Laplace transform of e to the minus st f of t plus g of t by the linearity of the integral of a sum is the sum of the integrals. This is the integral e to the minus st f of t dt plus the integral e to the minus st g of t dt. That's f of s plus g of s. So we see in this case that the Laplace transform of f plus g is the Laplace transform of f plus the Laplace transform of g. And this extends very easily to the sum of any number of functions whose Laplace transforms exist. So if we have functions f1 up to f sub n with the Laplace transform f sub I, defined for s greater than s sub I, then you let S naught be the largest, the maximum of S1, S2 up to S sub n. And for any numbers C1 up to Cn, if we take the linear combination of my functions C1 F1 plus C2 F2 up to Cn Fn, this Laplace transform is the sum of the Laplace transform C1L of F1 plus C2L of F2 up to Cn L of Fn. So this is, again, a basic fact about integrals, and in particular about Laplace transforms. So for example, we saw that the Laplace transform of e to the at is 1 over s minus a for s greater than a. Suppose I take what is called the hyperbolic cosine function, COSH, of some number bt. So the hyperbolic cosine is defined to be e to the bt plus e to the minus bt over 2. What is the Laplace transform of the hyperbolic cosine? That's the Laplace transform of this. What is this? This is 1/2 e to the bt plus 1/2 e to the minus bt. By linearity, this is 1/2 the Laplace transform of e to the bt plus 1/2 the Laplace transform of e to the minus bt. But we know what these Laplace transforms are. This is 1/2 the Laplace transform of e to the bt, that a equal b, you get 1 over s minus b. And the Laplace transform of e to the minus bt, you let a equal minus b, you get 1 over s plus b. And if you wanted to put this over a common denominator, this would be a half s plus b over s minus 1, s minus b, s plus b, plus s minus b over s plus b, s minus b. What is that? That's a half. You have a common denominator, s squared minus b squared. S plus b plus s minus b, the b's cancel, we get 2s. So we get s over s squared minus b squared. And this is valid for s has to be greater than b and s has to be greater than minus b, which means s is greater than the absolute value of b. So this is the Laplace transform of the hyperbolic cosine. Okay, so whenever you have a continuous function f, it always has a Laplace transform, unless it grows very, very fast. And if it's piecewise continuous, it also has a Laplace transform. Certainly if it's bounded, it will be fine. Yeah. Right. Any questions so far? Okay, so this was a review of chapter 8, section 1. And now I want to look at chapter 8, section 2. So section 8.2 is the inverse Laplace transform. And the problem is, given the Laplace transform of a function L of f, find f. And we say that f is the inverse Laplace transform of capital F. So here's an example of what we mean by an inverse Laplace transform. So that L inverse means you have the Laplace transform of something, let's say 1 over s squared minus 1. And L inverse of 1 over s squared minus 1, this is a function f of t such that the Laplace transform of f, which is the integral from 0 to infinity, e to the minus ft, f of t dt, is equal to 1 over f squared minus 1. That is, there's a function little f whose Laplace transform is 1 over s squared minus 1. Find the function. That is, find the inverse Laplace transform of 1 over f squared minus 1. And the quickest way to do this is to look at the table of Laplace transforms. 1 over s squared minus 1. Do we see anything like that on this right-hand column? 1 over s minus 1. Let's see, no. Here, 1 over, we have b over s squared minus b squared. So let me just write this down. So from the table, we see that the hyperbolic cosine of bt is equal to s. Sorry, that's true, but I want the hyperbolic sine. The hyperbolic sine of bt is equal to b over s squared minus b squared. That's from the table. So let me stop the share. So this is what I found from the table. In this, if I let b equal 1, I get that the Laplace transform of sinh, that's how we pronounce hyperbolic sine, sinh of t is equal to 1 over s squared minus 1. So that's the answer. If the Laplace transform of the hyperbolic sine of t is 1 over s squared minus 1, then the inverse Laplace transform of 1 over s squared minus 1 is the hyperbolic sine of t. So that's the answer to the problem. And just as the Laplace transform operator is linear, so is the inverse Laplace transform. So let's look at examples of functions that come up very often when we are solving differential equations, which is rational functions. So we have now the following problem. Find the inverse Laplace transform of 8 over s plus 5 plus 7 over s squared plus 3. And by linearity, I can write that as the inverse Laplace transform of 8 over s plus 5 plus the inverse Laplace transform of 7 over s squared plus 3. And again, by linearity, I can take the 8 outside. This is 8 times the inverse Laplace transform of 1 over s plus 5. And I can take the 7 outside of this, 7 times the inverse Laplace transform of 1 over s squared plus 3. And now I can look at my table. So from the table, I see that the Laplace transform of e to the at is 1 over s minus a, and the Laplace transform of sine omega t is omega over s squared plus omega squared. So if the Laplace transform of e to the at is 1 over s minus a, the Laplace transform, if I let a equal to 5, e to the 5t is 1 over s minus 5. oops, I'm sorry, e to the at, 1 over s minus a. So if I have e to the 5t, so the Laplace transform of e to the 5t is 1 over s minus 5, but I want 1 over s plus 5. So e to the minus 5t is 1 over s plus 5. So the inverse Laplace transform of 1 over s plus 5 is e to the minus 5t. What about 1 over s squared plus 3? So if I so here I have s squared plus 3. Here I have s squared plus omega squared. So here I want to let omega equal to the square root of 3. So that says the Laplace transform of the sine of the square root of 3 times t is the square root of 3 over s squared plus omega squared is 3. So the Laplace transform, if I divide by root 3, 1 over the square root of 3 sine of the square root of 3 times t is 1 over s squared plus 3. So the inverse Laplace transform of 1 over s squared plus 3 is 1 over the square root of 3 sine of root 3t. So I have this, and I have this. And I plug them into this equation. So I want to find the inverse Laplace transform of 8 over s plus 5 plus 7 over s squared plus 3. That's going to be 8 times this inverse transform, 8 e to the minus 5t plus 7 times this. So that's 7 over the square root of 3 times the sine of square root of 3t. So that is the solution to my problem. Again, I'm trying to do examples in the text, so when you're studying at home, you've seen this a lot, and you can work it out step by step and try to figure out what's going on. Okay. Any questions about this? Okay, let's keep going. This is all a lot of mathematical technique one has to master. Suppose we want to find the inverse Laplace transform of 3s plus 8 over s squared plus 2s plus 5. So this you don't find in the table, but we can write this. So let me just start to simplify this function. 3s plus 8 over s squared plus 2s plus 5. That's 3s over s squared plus 2s plus 5 plus 8 over s squared plus 2s plus 5. And if you look at the table, you see expressions for things that have denominators, which are like sort of a square of s plus something. So let's take this denominator, s squared plus 2s plus 5. I can write this. This is basically completing the square from high school algebra. This is s squared plus 2s plus 1 plus 4, because 5 is 1 plus 4. And s squared plus 2s plus 1, this is s plus 1 squared. And 4 is 2 squared. So I can write this as 3 times s over s plus 1 squared plus 2 squared plus 8 times 1 over s plus 1 squared plus 2 squared. And I do that because expressions of this form are in the table. Then you just have to look at the table and become familiar with the table. So let's look at the table again. I have, let's see, here is something which is s minus something squared, but just a plus s minus this in the numerator. And here is s minus something squared plus omega squared. So I have these two general formulas. Let me write them down and specialize them. See what happens. So stop share. So this is what I found in the table. That the Laplace transform of e to the lambda t cosine omega t was s minus lambda over s minus lambda squared plus omega squared. And the Laplace transform of e to the lambda t sine omega t is omega over s minus lambda squared plus omega squared. Okay. So now let's compare this with this. So if I let lambda equal 1, lambda equal minus 1, so then s minus lambda is s plus 1, and I let omega equal 2. So this is like, this is s minus lambda squared plus omega squared, except I need an omega in the numerator. So I would like this to be 2, so I can multiply 2 and divide by 2. 8 over 2 is just 4. Now this is a little trickier here. If lambda equals minus 1, I get s plus 1, and omega equal 2, I get 2 squared. But I need to have s minus lambda in the numerator, and I just have s. So I'm going to do something a little bit, I don't know, not sneaky, but it's what you have to do to survive. So I have, let me just write this down again. 3s plus 8 over s squared plus 2s plus 5. This is going to be a fraction over s plus 1 squared plus 4, 2 squared. And I have 3s in the numerator, and I want to have s plus 1. So I'm going to write this as 3 times s plus 1. So I've added 3 there, plus here I had 8 over s plus 1 squared plus 2 squared. So 8 is 3 plus 5. And if you check, so this is 3s over this, and this is 3 plus 5 over this, or 8 over this. So that's exactly correct. And now this, so the inverse Laplace transform of 3s plus 8 over s squared plus 2s plus 5 is 3 times the inverse Laplace transform of that, which is e to the lambda t, lambda is minus 1, times the cosine of omega t, 2t, plus Here I have 5 over s plus 1 squared plus 2 squared. I want a 2 in the numerator, so I want to write this as 5 over 2 times 2. So plus 5 halves, the inverse Laplace transform of this, which is e to the lambda t sine of 2t. Or if I want to factor out e to the minus t times 3 cosine 2t plus 5 halves sine of 2t. So you should have your book open on your computer and just take a look at this example on page 406, 407, 407. And ask me any questions you might have about it. Question? If not, then we will go on. And again, what we're learning how to calculate are Laplace transforms of rational functions. So let's take another example. So suppose we have a Laplace transform f of s equal to 3s plus 2 over s squared minus 3s plus 2. And we want to compute the inverse Laplace transform of f of s. So of course, what we can do with this is, again, there are lots of things, but we can notice the denominator factors. And then you can write this as partial fractions, a over s minus 1 plus b over s minus 2. And we need to find a and b. Of course, what makes this now very easy to do is we know that the inverse Laplace transform of 1 over s minus a is equal to e to the at. So the inverse Laplace transform of 1 over s minus 1 is e to the t. The inverse Laplace transform of 1 over s minus 2 is e to the 2t. So the inverse Laplace transform of this function f of s is going to be a e to the t plus b e to the 2t. But we still need to find a and b. So one way to do this is, there are lots of ways to do it. If you multiply through by s minus a, you will get 3s plus 2 over s minus 2 is a plus b times s minus 1 over s minus 2. And if you let s equal 1 in this equation, this is 0, you get a equals 3s plus 2, 5 over minus 1 or minus 5. And if you multiply this by s minus 2, you get 3s plus 2 over s minus 1 is a times s minus 2 over s minus 1 plus b. And if you let s equal 2 in this equation, you get b is equal to 3s plus 2 is 8. B is equal to 8. So the inverse Laplace transform of 3s plus 2 over s squared minus 3s plus 2 is equal to minus 5 e to the t plus 8 e to the 2t. And that's the answer. And in general, if you have a rational function whose denominator factors into distinct linear factors, the easiest thing to do is to expand that fraction into that rational function into partial fractions, solve for the numerators, and you'll get a linear combination of exponential functions. So let's look at another example, a little bit more complicated, but still the kind of thing that you need to be able to solve. This is example 8.2.5 in the text. So capital F of S is going to be equal to 6 plus S plus 1, S squared minus 5S plus 11 over S times S minus 1, S minus 2, S plus 1. So this is a rational function. This is a cubic polynomial over a quartic polynomial, but the denominator factors into distinct linear factors. Right? The denominator has roots minus 1, 0, 1, and 2. And so by the general theory of partial fractions, this is A over S plus B over S minus 1 plus C over S minus 2 plus D over S plus 1. For some numbers A, B, C, and D. And we want to find them. Well, this equals this. If you multiply through by S, you get on the left 6 plus S plus 1, S squared minus 5S plus 11 over S minus 1, S minus 2, S plus 1. When you multiply all this by S, you get A plus BS over S minus 1, CS over S minus 2, DS over S plus 1. If you let S equal 0, all of these terms become 0. So we just get A equal to what? And what is this equal to when S is 0? 6 plus 1 times 11 over minus 1 minus 2 times 1. That's 17 over 2. So A is equal to 17 halves. What happens if we take this equation and multiply through by S minus 1? We'll get on this side a B times terms that involve S minus 1. So when you let S equal 1, they all become 0, equals, you've canceled the S minus 1, it's going to be 6 plus S plus 1, S squared minus 5S plus 11 over S minus 2, S plus 1, evaluated when S equals 1. When S equals 1, this is 6 plus 2 times 1 minus 5 minus 4 plus 11 times 7 over, when S is 1, 1 times minus 1 times 2. So this is 14, this is 20 over minus 2, or minus 10. So B is equal to minus 10. If you multiply both sides of this equation by S minus 2 and let S equal 2, on the left, on this side, you'll get C equals, this term is gone. When you let S equal to 2, you get 6 plus 2 plus 1 is 3. When S is 2, this is 4 plus 11, that's 15 minus 10, that's 3 times 5. When s equals 2, I have 2 times 1 times 3, that's 15, that's 21 over 6, or 7/2. And then finally, if I take this equals this and multiply through by s plus 1, and then let s equal minus 1, I get d equals 6 plus 0. You let s equal minus 1, I get 0, over s equal to minus 1, minus 1, minus 2, minus 3. So that's 6 over minus 6, or minus 1. So A, B, C, and D are equal respectively to 17 over 2, minus 10, 7 over 2, and minus 1. And we've solved the problem. Now, this method works when you have a rational function whose denominator is a product of distinct linear factors. But you remember, perhaps, you should, or at least you learned this in Math 176, how to write a function as partial fractions in more general cases. So, for example, suppose the function f of s happens to be of this form, 8 minus s plus 2, 4s plus 10 over s plus 1 times s plus 2 squared. So we have a repeated factor here. This numerator has a polynomial of degree 2, the denominator has degree 3. So we can write this as a sum of 3 partial fractions, a over s plus 1 plus b over s plus 2 plus c over s plus 2 squared. Which means, now if you put this back over a common denominator, the common denominator is going to be s plus 1, s plus 2 squared. The numerator will be a times s plus 2 squared plus b times s plus 1, s plus 2 plus c times s plus 1. So these two fractions are equal. They have the same denominator. That means they have to have the same numerator. So a times s plus 2 squared plus b times s plus 1 plus c times, so s plus 1, s plus 2, plus c. Let me just write this a little bit more neatly. So I have a times s plus 2 squared plus b times s plus 1, s plus 2, plus c times s plus 2 squared equals this, 8 minus s plus 2, 4s plus 10. And we want to solve for a, b, and c. And a way to do that is just to pick good values for s and see what happens. So for example, that s equal minus 2, this is 0, this is 0. I get, this is c times s plus 1. Write it down properly. But that s equal minus 2, I have 0, 0, minus c equals 8. So c is equal to 8. But that s equal to minus 1, these two are 0. I get a times minus 1 plus 2, that's 1 squared, that's just a, equals when s is -1, this is 8 minus 1 plus 2 is 1. 4s, that's -4 plus 2 is 6. So a is equal to 2. How do I find b? Well, I just choose some number for s. Maybe I'll choose s equals 0. But at s equals 0, this is 4a plus 2b plus c equals, and when s is 0, this is 8 minus 2 times 10, that's 20, that's minus 12. Of course, 4a, a is 2, so 4a is 8, plus 2b, c is 8, plus 8 equals minus 12. That says 2b is minus 12 minus 16 is minus 28. b see, let me just double check what I did. I got c is equal to minus 8. Just write it down. C equals minus 8. This is a plus 2b minus 8 equals minus 12. So b is minus 12. So 2b is minus 12. b is minus 6. So the inverse Laplace transform is a 2 over s plus 1. Sorry. I'm trying to find, I have a Laplace transform of a function is 8 minus s plus 2 times make sure I write down my problem correctly. Yeah, 8 minus s plus 2 times 4s plus 10 over s plus 1, s plus 2 squared. And we know from the general theory of Laplace of partial fractions, this is going to be a over s plus 1 plus b over s plus 2 plus c over s plus 2 squared. And I just calculated a, b, and c. A is equal to 2. B is equal to minus 6. And C is equal to minus 8. And what do we know about our inverse Laplace transforms? We know that the Laplace transform, the Laplace transform of e to the at is 1 over s minus a. So here a is minus 1. So the Laplace transform of t over s plus 1 is going to be 2 e to the minus t. The Laplace transform of 6 over s plus 2 is going to be 6 e to the minus 2t. And what about 1 over s plus 2 squared? If I look at my table, I see that the Laplace transform of t to the n e to the at is n factorial over s minus a to the n plus 1. here I have 1 over s plus 2 squared. So if I let n equal to 1 and a equal to minus 2, this says the Laplace transform of t e to the minus 2t is n factorial, that's 1, over s minus a is s plus 2 squared. That's what this is. So this is the Laplace transform of 8 over s plus 2 squared is 8 t e to the minus 2t. So for my function f of s, the inverse Laplace transform of this function is 2e to the minus t plus 6e to the minus 2t plus 8t e to the minus 2t. And that's the answer. All right. So that is the general method for dealing with inverse Laplace transforms. This is section 8.2 in the text. And you should have at hand all the time the table of inverse Laplace transforms. You don't need to memorize it. There's no reason to memorize it. You should be able to calculate some Laplace transforms. But if you simply have to find the Laplace transform of one function or the inverse Laplace transform of another function, don't hesitate, use the table. Okay. That is the lesson for today. Any questions about this? If not, it's a chilly day outside, but that's fine, I guess. Everyone be well. And we have a class on Wednesday, day before Thanksgiving somehow. So our next class will be on Wednesday. Okay. Bye all.